And welcome back, everyone. Thanks for joining us again on this beautiful Wednesday. It's now been a couple days since the test. Looking at your grade is over, and now it's time to think about what you want to learn from that first test experience. People who take time to reflect learn better and usually earn higher grades as well. So taking time to reflect on how that test went, now that the initial experience is over, is worth your while. Sometime this week, I encourage you to think about what went well. Which types of questions went well? What didn't go so well? Was it time management? Can you find a pattern in the types of questions that you may not have gotten correct? And based on what you can learn from this test one experience, what do you plan to do this month to be ready for test number 2? Taking time to reflect and think about what you can learn from this experience is going to help you as you move forward. Okay, so we have learned about VSEPR theory. So valence, shell, electron, pair, repulsion. Electron pairs, whether they be bonding, single, double, or triple, or non-bonding electrons, try to get as far away from one another as possible. We need to count the number of electron groups around the central atom, and that will help us to determine the electron arrangement. Whether it's linear, we have 2 groups as far away from one another as possible, or trigonal planar, 3 groups as far away as possible. And we've learned how to use our model kits as we go along. We have a couple examples to wrap up our discussion of VSEPR. Then we're going to apply that in 3D shapes and looking at polarity, and then we'll be jumping into 3.3 today as well. So we're going to jump in on 3.2.6. Here we want to draw the Lewis structures of a few different compounds and predict their shapes. Now, Lewis structure was earlier in this chapter, so I've gone ahead and drawn these Lewis structures already. Based on what we've already talked about, you should also be able to draw these groups. What we're going to do is jump in and count the number of electron groups, and from the electron arrangement, figure out molecular shape. So with my sulfur hexafluoride, I can see I have 6 electron regions. We could classify this as AX6. All of them are bonding, so therefore this must be an octahedral shape. The electron arrangement is octahedral. All of these regions are bonding, so the shape is also octahedral. But then we go to XeF4. And here, this is an example of an expanded octet. You can see the central atom xenon can claim 8 electrons from the 4 bonds, but plus an extra 4 electrons. So that gives us 12 valence electrons. It has an expanded octet. It's big enough to do that. So if we count number of bonding regions is 4, non-bonding regions is 2, that gets us to 6 regions of electron density. So that means we pull out that pink shape that has 6 regions of electron density. We can also write the ax notation. We can see 4 bonding regions, or 4 atoms bonded to it, and 2 pairs of non-bonding electrons. 4 plus 2 gives us 6 regions of electron density. So we pull out that pink shape from our model kit. We're not going to use that one as much today, but the first region that's non-bonding, we can grab that anywhere. It doesn't really matter. They're all the same. But then when we take the second region of non-bonding pairs of electrons, we're going to grab that from the opposite side where the first non-bonding pair of electrons are. Non-bonding pairs of electrons like to have as much space as possible compared to bonding electrons. So if we have 1 non-bonding pair on the bottom, 1 non-bonding pair at the top, what shape do we have left? Turn to the person beside you and tell them what shape that is. Awesome. Square planar. Okay, so I'm going to leave this one up, and my question for you is, which of the following are correct for the final compound ClF5? Draw the Lewis structure, figure out its electron arrangement and its molecular shape. Work with the person beside you for 1 minute. And we now have the Lewis structure on the screen, so you can move on to electron arrangement and molecular shape. And 10 more seconds. And 3, 2, and 1. Okay, 3/4 going for D. We have an octahedral electron arrangement because we have 6 regions of electron density. One of these regions is a non-bonding pair of electrons, so we could classify this as AX5E1, which tells us we have a square pyramidal shape. So I'm going to use my document camera over here. Since I have 6 regions of electron density, I'm going to grab my pink structure that has 6 prongs on it. One of the regions is a non-bonding pair of electrons, so I hide it with my hand and I pay attention to the remaining atoms that I can see. If I look at it this way, I can put all 4 of these prongs on a plane. That gives us a square. And then we have one prong pointing up, which gives us a square pyramid. So that's why this is called square pyramidal. Now we can draw this in 3D, and we need to be able to draw this in 3D. One way to do that is to draw the chlorine with the fluorine pointing up, the non-bonding pair of electrons pointing down, a fluorine coming towards us and away from us, and towards us and away from us. That's one way to visualize drawing the 3D shape of the square pyramidal. We could draw it sideways, upside down. There's not one right way, but we can see 2 fluorines coming towards us, 2 fluorines away, and 1 fluorine going up. I'm going to back up to the previous question because we didn't draw the 3D structures of these ones. So for my sulfur hexafluoride, I can draw the sulfur at the center, fluorine coming towards me and away from me, and towards me, and the fluorine going straight up on my paper and straight down on my paper. So practice holding the shape and drawing it on your paper. It's also handy to be able to rotate it and draw it a different way using the wedges and the dashes. For the square planar, we could draw it just as we see on the screen. If I take my structure here and turn it towards you, it's like you're looking straight down a lone pair of electrons and you see the 4 prongs lying in the plane of your paper. The XEF bonds can all lie on a plane. So we would call this a planar molecule, which is where the square planar comes through. If you want it to be really confusing, well, not really confusing, another way that could also be legitimate is to look at it sideways. And then that means we're looking at it this way. with the non-bonding pair of electrons up and down. So you could lie it on your page, draw it that way, or you could look towards it this way. And we need to be able to visualize and manipulate these molecules and draw them different ways. And as you go on in science, you want to be able to determine when molecules are the same or different. And having your model kit, being able to rotate it and draw it a different way, is going to help you out. Okay, well done. Let's keep jumping along here. So you now come to this big table that's a great summary of what we've talked about. We have identified 2 regions of electron density, and that gives us our linear shape. And we have built that with our model kit. If we have 3 regions of electron density, well, it could be trigonal planar or bent, depending on if we have 0 or 1 pair of non-bonding electrons. And it's built around that trigonal planar model kit. So, into your kit, you have your linear option, 2 regions of electron density. Your trigonal planar, 3 regions of electron density. Your tetrahedral, which is 4 regions of electron density, which somehow didn't make it onto my slide. It's in your table. And then 5 regions of electron density, where we get to our trigonal bipyramidal shape. And then 6 regions is our octahedral. And then we can figure out the molecular shape based on these electron arrangements. So I would encourage you, make a little kit of 2, 3, 4, 5, and 6 regions of electron density, because all of the shapes that we do in this course can be built from one of these shapes. So we can start with our octahedral, turn it into square pyramidal, turn it into square planar, and it's all built on these shapes. You can bring these into the exam with you. So I would encourage you, make yourself a little set, and you have all the electron regions covered. Now, you will see in this table that we also have hybridizations mentioned. And we haven't taught hybridizations yet. You may remember this from high school, but we're going to get to that after our intermolecular forces. So when we get to hybridizations, we're going to see how these ideas link together. For now, you can ignore it here. Okay, so we've talked about how we can identify the shape with the central atom and the atoms that are bonded to it, the electron regions. We can also identify the shape around one atom in a larger structure. So that's what we're going to do here. We're going to wrap up this conversation on shapes by identifying the shapes around the indicated carbon and oxygen in this larger molecule that we started with in this topic. Okay, so chat with the person beside you, identify the shapes around those atoms. And 10 more seconds. And 3, 2, and 1. Okay, so 81% going for D, and I agree. We have 4 regions of electron density around this carbon. They're all bonding, so that shows us we have a tetrahedral shape. Oxygen has 2 non-bonding pairs of electrons, giving it a bent shape. So well done. Okay, we're now going to move on with our conversation of shapes to wrap up topic 3.2. And we're going to combine that with our discussion of bond polarity. We already know how to determine if a bond is polar. If there's an unequal sharing of the electrons, then we have a polar covalent bond, as long as it's not an ionic bond. That's really unequal sharing. That's a whole transfer. But if we have a covalent bond and the electronegativity difference between those atoms is big enough that they don't share equally, so bigger than like 0.4 difference, so bigger than a difference between carbon and hydrogen, pretty much everything else is going to be polar if it's a covalent bond of different atoms. We know how to identify polar bonds. We now need to connect that to polar molecules, because this concept actually matters even more than polar bonds. If we have polar bonds, we may have a polar molecule. But even with polar bonds, we may not have a polar molecule. It depends how the pull of these vectors, of these different yanks on the electron density in different three-dimensional space, sums up for the whole molecule. So if we have a polar molecule, that means we have polar bonds, and the sum of the vectors, the sum of the pull of all of those bonds, results in an overall pull in one direction on the molecule. So we could have a polar molecule. It's going to have a net dipole, a net pull of electrons towards one part of the molecule. In contrast, we could have a nonpolar molecule. This is when we have nonpolar bonds, or if we have polar bonds that are being pulled in equal and opposite directions. So to figure out if we have a polar molecule or not, we need to think about these vectors. So we're going to do some math addition. We're actually not going to do the math. We're just going to look at sizes and add them up that way. But you could do the math. You could do the 3D graph paper, adding different vectors and X, Y, Z, and that is why it works. So for some examples of non-polar molecules, here we have carbon dioxide on the left. Oxygen is more electronegative, so it is pulling that electron density towards itself. But we also have another oxygen pulling that electron density exactly in the opposite direction. Carbon to oxygen this way and carbon to oxygen that way is an equal and opposite pull because, according to Vesper theory, we have a linear shape. If this wasn't linear, if it was bent, then it wouldn't be equal and opposite. But since this is linear, we have 180 degrees between carbon to oxygen and carbon to oxygen. It nets out as 0, and we have a non-polar molecule. Same with this tetrachlorocarbon molecule. We're going to look at that one in a minute. And this benzene molecule that has a carbon-chlorine bond pulling it this way and a carbon-chlorine bond pulling it this way, if we take this vector and then add head to tail, the other vector, we're back to where we started. When you add vectors, you add heads to tails, and you can see they come back to 0. So we have polar bonds, but they're pulling in equal and opposite directions. So I would like a couple volunteers to do a really short demo. Do I have a volunteer? You're just going to pull on something. Okay, 1, 2, 3, and 4. Come on down. Yeah, you can give them a hand. Come on. Okay. Now, you're going to be really gentle because I have some kind of flimsy ribbon here and you look like you could actually do tug of war quite well. Okay, we're going to start with 2. So you can grab these 2 pieces here. So just grab both there. And you can grab both here, and I'm going to get the 2 of you in just a second. Okay, so here I have the central atom. You can keep these together. We're going to pretend it's one ribbon. Yeah. So I'm going to let go in a second, and you're both going to equally pull on the electron density. So I'm the central atom. Very gently. Please don't break my ribbon. Okay. You're more electronegative than me, and you're more electronegative than me. So you want the electron density. You want it, but you both have the same electronegativity. Okay. There we go. The vector this way and the vector that way are the same. Excellent. Okay. Now I need you to come in and join. Now we have a trigonal planar structure, and then I'm going to have you slide this way so people can still see. Now I'm going to get my trigonal planar model kit, and I'm going to lay it over here. Ooh, well done, 120 degrees for each one. All of you are more electronegative than me. You're all pulling on my electrons, but you're pulling equally in opposite directions. So on the count of 3, you can each pull, and nothing happened. Your pull and your pull and your pull, if we add those vectors, if we take this ribbon and that ribbon and this ribbon, they all add up together. Okay, can you grab the 4th string there? I'm going to get my tetrahedral shape. So now this one's a little trickier. See if you can match the tetrahedral shape. So one person's going to need to go straight up. We need 109.5. Well done. Okay, there we go. In 3-dimensional space, the up from this vector is going to cancel the 3 small downs from those vectors. We still have a triangle, and those vectors cancel out. Okay, so equal and opposite poles, they're all pulling on the ribbon. They all have greater electronegativity than me, yet nothing changes. Okay, now stay there for a second. We're now going to move to this molecule here. Now, I'm sorry. You are now hydrogen. Nope, you're not hydrogen. You're chlorine. Chlorine's pointing up. You're hydrogen. Okay. So the 3 of you are hydrogen, or 3 of you are chlorine. You're hydrogen. You don't have as strong a pull. So on the count of 3, the 3 of you are going to pull hard, and you're not going to pull hard at all. Okay? Ready, set, go. Whoa, it totally moved. We now have a net dipole, pulling in that direction. Okay. Now, let's see. Up is chlorine. Back is chlorine. Both of you are hydrogens. Okay, so the 2 chlorines you get to pull hard on the count of 3, and hydrogens you don't pull at all. Ready, set, go. Whoa, it totally moved. We now have a net dipole pulling that way. We have a polar molecule. Okay, and now go back to the center. Well done. So now chlorine is up. You're the only polar bond. Hydrogens, you don't get very strong. Ready, set, go. Whoa, we totally have a net dipole pulling up. Okay, give them a round of applause. Well done. And do you want a tweet? Thank you.
Thank you.
Okay, so we have demonstrated the vector polarities, the pulls on the electron density. Tetrahedral, 3-dimensional space, if it's all polar, equal, it's a non-polar molecule. However, when we have an unequal pull, all of those arrangements are polar. The vector poles do not sum out. Okay, so then we move on to the polar examples you have in your workbook. So water is an example of a polar molecule. Oxygen is more electronegative than hydrogen. Oxygen is more electronegative than hydrogen, and those non-bonding electrons are not pulling in any direction. So we have a net dipole up because we have this direction, and so we have a net pull up. Here with nitrogen, we have a non-bonding pair of electrons. Nitrogen is more electronegative, and it's pulling the electron density from all of the hydrogens. So we have a net dipole, again, pulling up, giving us a polar molecule. And you have an electrostatic potential map of this one. So we have slightly positive and slightly positive hydrogens and a slightly negative nitrogen. And this makes a polar molecule. So it can interact with other polar molecules. Here we have one more molecule, and I'm going to ask you to redraw this one. I'm going to rotate it so the 2 chlorines are in the plane of your paper, and the hydrogens are coming towards you and away from you. So it's the same thing. I just took the chlorine that's coming towards you on your left and rotated it. So it's the same molecule, just the 2 chlorines are now in the plane of your paper, so that we can see the net pull towards chlorine and the net pull towards chlorine. And if we add those arrows together, we're going to get a net dipole pulling the electron density that way, giving us a polar molecule. And again, we have an aromatic group with chlorines, giving it a net dipole towards that side of the molecule. So to get a polar molecule, we need polar bonds, and we need the net dipole to be not zero. They can't cancel out. Okay, so chat with the person beside you. How many of these molecules are non-polar? And 10 more seconds. And 3, 2, and 1. Ooh, half of you identified one, and that is the correct answer. Let's chat about this. Okay, I'm going to start with our trichloromethane. We have 3 chlorines, each with a partially down vector, pulling that electron density towards the bottom of the molecule. Hydrogen can't balance that down pull. So this is polar. Fluorine is very electronegative. Chlorine is pretty electronegative, but we have an unequal pull on this molecule. Fluorine is more electronegative, so the magnitude, the size of that vector pull this way is bigger than the pull this way, so we have a net dipole. So this is also polar. For here, we need to recognize the shape for this one. We have 5 regions of electron density in this Lewis structure, which tells me I need to pull out my trigonal bipyramidal shape. 2 of these regions are non-bonding, so I pay attention to what's left and I see it's T-shaped. The electron density pull this way is equal and opposite to the electron density pull this way. So these factor out. But the electron density pull towards the 3rd fluorine is not balanced out by the non-bonding electrons. So we do have a pull in this molecule, making it polar. This is where having your model kit is really helpful. And then the final one, equal and opposite, making this a non-polar molecule. And that's our 1 out of the list. Okay, so we have to combine some topics to be able to solve these problems. Figure out which bonds are polar or not, and apply that to the shape and pay attention to the vector pulls of that electron density. Why do we care if a molecule is polar or not? Well, that has a huge impact on boiling point and melting point and the way that molecules interact, which brings us to intermolecular forces. To kick this off, I have a question for you. What happens to water molecules at 100 degrees Celsius under atmospheric pressure? So like in your kitchen in London, Ontario. Chat with the person beside you for 1 minute and submit your answer. And 10 more seconds. And 3, 2, and 1. Okay, E is the most popular, but B had a lot of votes as well. Okay, so let's look through these options. If this is a multiple choice test question, how would we figure this one out? Electrons are excited to higher energy orbitals. Well, that's how we have absorption and when they come down, emission, but that's not what's happening when water boils. Covalent bonds between oxygen and hydrogen are broken. This is a very common misconception, and it's not the case. Here I have a water molecule. Here's my oxygen and my hydrogen, and these are just my 2 non-bonding pairs of electrons on oxygen. When water boils, it was a liquid state, so molecules kind of passing over each other, pulled together by their intermolecular forces, their attractions. When they boil, they turn into gas, and so it's all by itself and floating around. So the attractive forces between molecules is overcome when water boils. We're not breaking this bond and have hydroxide and atomic hydrogen. That would be very dangerous. You wouldn't want to be breathing in the steam if that was the case. Steam, when your kettle boils, is just water that's a gas. So it's still H2O. It's still water. It's just separated and moving at a fast pace as a gas rather than a liquid, rather than locked in as a solid. So we're not breaking covalent bonds. We're breaking intermolecular attractions between adjacent water molecules. So that's what intermolecular force is, and that's what this topic is all about. So starting with propane. Here I have 3 carbon atoms, C, C, C. Remember, the end of a line counts as a carbon, a bend in a line counts as a carbon, and the end of a line counts as a carbon. The prongs that don't have anything on them, I'm considering now that these are my hydrogens. So I have 3 hydrogens on the first one, 2 hydrogens on the next, and 3 hydrogens on the final. So CH3, CH2, CH3. This would be propane. This is what's in your barbecue tank. Propane interacts with another propane molecule, and they are attracted to one another with very weak forces. However, the force is enough to keep them together as a liquid up until a certain temperature, until that temperature is overcome, and then they turn into gaseous molecules. But notice, it's still propane. We haven't popped a bond and broken a bond, or broken and reformed a bond. We're just separating these molecules from one another. The covalent bonds are staying intact, but we're disrupting the attraction between these molecules. So intermolecular forces is between molecules that are beside each other, not covalent bonds. And this has a huge impact on boiling points, BP, and melting points, MP. If we look at this little table here, if we started with a solid and we bring it up to its melting point, that means that solid turns into a liquid. And if we heat it up again to its boiling point, that means we've turned it into a gas. My propane example, it melts at negative 187 degrees Celsius. There's no way my backyard gets that cold in London, Ontario. So propane doesn't exist as a solid pretty much ever where I live. It exists mostly as a gas, but even if it was a liquid, if it's colder than negative 42 degrees Celsius, which we might get a day or two like that this winter, probably not. So most of the time, propane exists as a gas. That's why it's in a pressurized container because it's a gas and it would expand at atmospheric pressure. Once we get over -42, like the coldest day you could imagine, propane is actually a gas, and we don't have these attractive forces between molecules. They've been overcome, and the molecules are moving at fast speeds. Propane has one type of intermolecular force. Meanwhile, dimethyl ether has a different type of intermolecular force. And you can see the boiling or the melting point has increased, and the boiling point has increased as well. We have to put in more energy to overcome these attractive forces between molecules. When we get to ethanol, the type of alcohol that is in beer or wine, we have a much stronger intermolecular force, such that you have to get this to almost 80 degrees Celsius to turn it into a gas. Which means if you cook with rum in your baking, that does evaporate away because your oven is hotter than 78 degrees Celsius. But propane boiling at -42 versus ethanol boiling at almost 80 degrees Celsius, that's a huge temperature difference. We have to put in a lot more energy to disrupt the intermolecular forces between ethanol molecules. And so we're going to talk about what those forces are. So we're going to start with dispersion forces. These are the weakest force, but they're still quite significant. When I think about dispersion forces, I think about Jell-O. Does anybody like Jell-O here? Okay, so some people, you don't have to like Jell-O, that's okay. But here I have some Jell-O, and if you've ever played with Jell-O, it's very wiggly, right? So when I was little, a birthday party wasn't a party until you had Jell-O jigglers, and it was very cool to make Jell-O jigglers, okay? So when you think of Jell-O jigglers, I'd like you to think about dispersion forces, okay? So here's my Jell-O jiggler. You can see it's kind of like jiggling all around, right? It's not staying. This reminds me of the electron cloud around a molecule. It's not like a Lego brick that's solid. The electron cloud is jiggling all over the place. So one moment it's here, one moment it's there, and it's kind of jiggling all over, which means the nucleus at the center of this molecule is going to be, more accessible or less accessible depending on where in the jiggle we are, okay? So we have a temporary distortion in the electron density, like every couple seconds, happening all the time, that's jiggling all over. For a moment, we might have a little bit of extra electron density hanging out on this side of the molecule, over here with our methane. For not permanently, but just for a moment, it jiggles this way. That induces a slight positive in the molecule next to it, just for a second. And then a second later, it jiggles the other way and distorts slight negative over here, which induces a slight positive over here. So it jiggles and joggles and has these temporary weak attractions between molecules. As the molecule gets bigger, I think this is going to get messy. As the molecule gets bigger, we have more opportunity for distortions and for more wiggles and more attraction between molecules. So if we have a bigger molecule, we just have more opportunities for more attractions between those molecules. So if we compare, let's look here. We have methane, two pretty small molecules, carbon with 4 hydrogens around it, tetrahedral shape, right? So imagine, I could probably stick these in Jell-O, but I wouldn't want to clean that up. So imagine the Jell-O is like squiggly all over this. They have temporary slight distortions in their electron density that attract them to one another. But if we look at pentane, I need something bigger now. Let's add 2 more hydrogens to my propane to turn it into pentane. Do you see how why we have that zigzag structure for organic molecules? You can see how we're building on that because the carbon atoms, when they have single bonds, they have that tetrahedral shape, which gives us these zigzag, which why each carbon in the bend is a carbon. Well, we now just have so many more opportunities for attraction between these molecules. We could have a jello jiggler here, and a jello jiggler here, and a jello jiggler here. So more attraction. So what's the takeaway? Greater surface area means greater dispersion forces, which means stronger attraction. You could predict the boiling points and see you're going to have to put in a lot more energy to pull two pentane molecules apart compared to pulling methane molecules apart. 0.05 to about 10 kilojoules per mole, so small. We could also look at surface area when the molecules have the same molecular formula. Here, I have what we call normal pentane. It has 5 carbon atoms there. This molecule also has 5 carbon atoms, but it's called neopentane because the central carbon is connected to 3 other carbons. I'm going to walk around with this. Here, you can see I have a lot of surface area for attraction between these 2 normal pentane molecules compared to these ones. They have surface area attraction here, but these parts aren't interacting with one another as much. These molecules have a smaller surface area to have these temporary distortions, those dispersion forces, compared to my normal pentane that just has a greater surface area. Bigger surface area means more attractive forces, greater dispersion forces. So you could predict the boiling point for that one as well. Okay, let's move up to our next type of intermolecular force. And this is when we have a polar molecule interacting with a polar molecule. We just talked at the end of topic 3.2 to identify those polar molecules. Oxygen is more polar than carbon compared to carbon to carbon. So we have a net dipole. This molecule is polar. It has a permanent delta negative, which means the other side of the molecule has a permanent delta positive. So it's not just like a jello jiggler distortion, it's always that way. Might have like slight jiggles over here, but we always have more electron density around the more polar atom. When we have 2 molecules that are polar, notice it's polar molecules, not just polar bonds. We have to think about the sum of the vectors of the attractions. Polar molecules can undergo dipole-dipole interactions. These types of interactions, because they're permanent, they are stronger. Thumbs up if you remember dipole-dipole from high school. Okay, this is review. Excellent. And if you don't, now you get to learn the terms. Okay, and now we move on to hydrogen bonding. Hydrogen bonding is a special type of dipole-dipole attraction. It's when we have a molecule and it has such a strong dipole, meaning that we have a polar bond in this molecule that is either fluorine to hydrogen, or nitrogen to hydrogen, or oxygen to hydrogen. Fluorine, nitrogen, and oxygen are so electronegative, when they bind to hydrogen, it's a very big difference in electronegativity difference. We end up with a very polar part of that molecule, and it undergoes a special type of dipole-dipole interaction called hydrogen bonding. Fluorine, nitrogen, or oxygen is very electronegative, which makes the hydrogen that it's attracted to, it doesn't even have a hope, a chance. It's just really not as strong at pulling those electrons. So it's partially positive. And then we have our fluorine, nitrogen, or oxygen in another adjacent molecule, so a different molecule beside it. It has a lone pair of electrons, and that lone pair of electrons on the electronegative atom, fluorine, nitrogen, or oxygen, is attracted to this partially positive hydrogen. And that attraction results in hydrogen bonding. So hydrogen bonding is important. All of these bonding things are important, all of these intermolecular forces. Hydrogen bonding is especially important in your DNA, where we have guanine and cytosine. Here we have nitrogen with a partially positive hydrogen being attracted to one of the lone pairs of electrons of oxygen on another nucleic acid. And we have a lone pair of electrons being attracted to another positive and lone pair of electrons to another. So we have 3 regions where hydrogen bonding is happening between guanine and cytosine. You may remember the other 2 nucleic acids are combined by 2 hydrogen bonds, so they're not quite as strong. But these hydrogen bonds are so strong, this is what keeps your double helices attracted to one another and held together. So we have dispersion force is the weakest, but still very important, dipole-dipole, which is stronger, and hydrogen bonding, which is the strongest. And that's going to help us predict boiling points, so when we come back on Friday, we will do that. Have a great day, and I will see you then.